Uh, Hello to everyone, and today I'll be discussing that the molecular polarisability. Before going much in detail of the rotational Raman spectra and the vibrational Raman spectra, let me get back to this topic, that is molecular polarisability. While I was discussing that the classical theory of the Raman effect, there we have discussed about the molecular polarisability. And again, to understand it, we need to understand a little bit about the structures of the molecules to estimate, to reconstruct, to study the structure and the spectra of the molecules, rotational and the vibrational spectra. As we have already discussed that the classical theory of the Raman effect not wholly adequate, and it is a worth to consider this classical theory to understand the concept of, to understand the spectroscopy, and it provides or it to understand the polarizability of the molecule. So when a molecule is put in a static field, what happens that the nuclear charge, that is positive charge, attracts to the negative side of the field, and the positive or the negative charge attracts towards the positive positive field or positive pole. So the separation of the charge centers, the separation between the charge centers causes the induced dipole moment, and this material is called the polarized. Then the size of the induced dipole moment, that is P or the mu, depends on both the magnitude and the applied field E. So simply we could write this induced dipole moment P is equal to alpha of E, where alpha is your polarizability. For example, simplest example for a diatomic molecule H2, so you have H of H, simple diatomic molecule. As the polarizability is anisotropic, the electrons forming a bond are more easily displaced by an electric field applied along the bond. Means once I am applying field across this bond, then it displaces charge more. And even that, if you will see that if I am looking that along the direction of this bond, if I am applying a field, it is inducing the polarizability or the induced dipole moment. And it is just, if I will apply a field across this bond, then in the simple diatomic molecule, we'll see that experimentally it can be found from the spectral lines, the intensity of the spectral lines of the rotational spectra. Then if I'm applying across this one, across this bond, then it is just a half of it. And in between, the induced dipole moment will be the, if the x is along, if I'm going along this direction and perpendicular to this one, across this one, or in between if I'm applying the field, then I will be just in between the one time or the two time. In between the field induced polarizability will be that much. So for the simplest case of this H of H or this H of this H, simple diatomic molecule. We can represent the polarity in various directions, most conveniently by drawing a polaristic ellipse. So the best way is to represent as a polarity ellipse. So once I will plot the polarity ellipse, then for this one I will be getting somehow this kind of the polarity ellipse. If I am applying the across, then I will be getting that polarity ellipse in this fashion. So where this ellipsoid is a three-dimensional surface whose distance from the electrical center of a molecule, which is also a gravitational as well, is simply proportional to 1 upon under root alpha I. Alpha I is a polarity along the line joining at I point suppose I have some I point over here, then the polarity depending 1 upon under root of alpha I. If this is the higher, then the polarity will be the less. If it is a smaller, then the polarizability is the high. It means that from here it is very clear that if I'm applying the field along this direction, then I have this alpha under 2 upon alpha L very small, then the total polarizability will be the higher in this case. If the polarizability is the higher, means the induced dipole moment value is higher. So since the and even now if I'm applying the across, we'll see that the cross section of the diatomic molecule, if I'm applying the perpendicular direction to this, then the polarizability ellipse is almost, it is circular because the cross section is the circular one. In the all direction, perpendicular to this axis, perpendicular to this bond axis, if I'm applying the field in all the way, I'm getting the same polarizability. That is why I'm getting that for the diatomic molecule simple circular cross section. And the polarizability of a diatomic molecule is the same for the all direction at right angle to the bond axis. Bond axis, perpendicular to the bond axis. The ellipsoid has a circular cross section. The ellipsoid has a circular cross section. So for example, another diatomic molecules like CO, HCl, or a linear polyatomic molecules like CO2 and C2H2 means that CH of triple bond of CH. So all these such molecules, linear polyatomic molecules, diatomic molecules, if we are looking at, will be having the same kind of the ellipsoid. Along the bond axis, I have a ellipsoid, and perpendicular to this one in the all direction, I'll be getting the circular one. For these molecules, you may have the value of the major axis and the minor axis may vary, but the shape will be remaining the same for the simple diatomic linear molecules. Now, this is a simple diatomic molecule. Then we'll see that the symmetric top molecules and other sort of the molecular structures. Now, as we have discussed that if applied field is E is equal to E naught of sine 2 pi of nu prime is the incident frequency, nu prime of T. So if it is induced dipole moment, this P is equal to or mu, some textbooks it is represented by mu and somewhere it is P, then is equal to alpha of E is equal to alpha of E naught sine 2 pi of nu prime of T. Means that if it is a case, then your dipole is oscillating with the same frequency of the incident, that is the exciting frequency, and this is called my Rayleigh lines. Now, as we know that molecule having its internal motions as well. For example, it's a rotation and the vibrations. If the rotations and the vibrations are also altering that the polarity, then there must be this polarity, this mu alpha must be the function of my rotational frequency and the vibrational frequency. For example, I'm considering a case when you have a vibrational case, then this alpha is equal to alpha naught, that is the what its field is producing. Or if you remember, we wrote this alpha naught of vibration plus alpha 1 of vibration of sine 2 pi of V vibration of T. Now once I will put this value alpha in this relation, then you have this mu is equal to alpha naught of V plus alpha 1 of V sine 2 phi of V vibrational of T and into of this E naught sine 2 phi nu prime of T. Simply once you will be solving it, then you will be getting that this alpha of naught vibrational E naught of sine 2 pi of nu of T plus alpha 1 of nu E naught divided by E naught and the sine 2 pi of nu prime of t into sine 2 pi of nu vibrational of t. Once we will be solving it, this term already we have computed is 1 of the E naught divided by 2, and this is again this cos of 2 pi nu prime plus of this sine A plus sine B, sine A into sine B. Then you have nu vibrational of T minus cos 2 pi nu exciting minus nu vibrational of T. So you have the Rayleigh scattering, you have a anti-Stokes line, and you have a Stokes lines. And in a similar fashion, once we will be doing that for the rotational spectra, you will be getting that is 2 pi 2 nu of rotational and a minus 2 of nu rotational. The reason is that because if the polarity is altering, that is polarization is changing along the axis of this polarization, in a one rotation the polarity is changing the twice, because along the axis it is the same, that is why the frequency is doubled. So I'm not writing that one. So what it suggests that so now simply this is the frequency, simply you are getting that is mu is equal to, or the component for these frequencies are coming this at the output, nu vibrational Raman is equal to this nu prime, that is the nu prime, plus minus of nu vibrational. So what exactly you will be getting at the output? You have an additional this new exciting frequency plus minus of nu vibrational, Stokes and the anti-Stokes lines. So if you look at it carefully, that it means that if the value of this alpha 1 of nu is equal to 0, if your vibrational frequency is not altering your polarisability, then is simply you are getting only this term. It means that is the Rayleigh line. So we may have a such kind of the material where this my rotational frequency or the vibrational frequencies are not altering my polarisability. In that case, simply you are getting the Rayleigh scattering. Rayleigh scattering means that there is no shift in your Raman, and there is no Raman shift at all. So now, in order to active a molecular rotation or the vibration must cause some change in the component of the molecular polarisability. So to study that one, there must be some change in a molecular polarity. A change in a molecular polarity is of course reflected by a change in either the magnitude of the dipole moment or the direction of the polarity ellipse. Either it is altering the direction of the polarity ellipse or the magnitude is changing. So what we could say that at this point, its rule should be contrasted that what we have, if you remember, that in infrared spectroscopy and the microwave, that is the rotational spectroscopy, which suggests that the molecular motion must produce a change in electric dipole of the molecule. So this rule should be contrasted with that of infrared and the microwave activity, which is that the molecular motion must produce a change in the electric dipole of the molecule. Now, I am considering another polarized ellipse for a complicated molecule. For example, triatomic molecule, that is H2O. So you have H2O, H of H, O, H, 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 O of H. It's a triatomic molecule H2O. So by analogy with what we have discussed about the just a diatomic molecule H2, then we could think that you have one polarizability ellipse across this one, another one is across this one, which is not true, but with the analogy of the H2 diatomic molecules, we could think that we can predict that we have these kind of the two ellipses, but it is not true. And the reason is that, and other thing is that if I'm applying a certain field, if I'm talking about that the static field like my visible or ultraviolet, then the range of this frequency is, or the wavelength is 1 micrometer to 10 nanometer. However, the dimension of the bond is 0.1 nanometer, 1 angstrom. Means that at this point, it means that if I'm applying a field, it is not probing a polarity of this bond, because even I'm using the hard X-ray itself, even that this frequency and that wavelength won't be altering the polarity across this bond, along this bond. Rather, it only it sense, this field only sense or change the shape of the polarizability, not probing the it's a across this your bond, because the size of the wavelength is very higher as compared to my bond length. So it means that it is just a sensing that it overall polarity ellipse. It is deforming, it is changing its orientation or the direction of the polarity ellipse. So most of the cases, either you may have the ellipsoid structure of the circular one. So for example, in this case, so in the case of the H2O molecule, the polarizability is found to be different along all the three major axes of the molecule, which the line is the molecular plane bisecting the HOH angle at right angle to the. So I have this axis. So now the field is along this direction, then perpendicular to this one and perpendicular to the plane of this one. So you have the three categories now, three things now: across, perpendicular, then it's the plane perpendicular to this one. So if I will plot it these ellipse, then you have this structure, and here you have much. Now, if you look at, if I have field axis bisecting this angle, then perpendicular to this one, then the perpendicular to the plane of this one, then you have a different polarities. Now, as I said that this total polarity will be the distance, that is 1 upon under root of alpha I. So in this case, the polarizability will be the moderate. In this one, it will be the minimum. In this one, you will have the maximum, because along the boundary itself, you have the polarizability. So all three of the ellipsoid axes are also different. The ellipsoid, it is represented in this fashion. Other such molecules are H2S, SO2. Have a similarly shaped ellipsoid, but with different dimensions. Of course, because their charges are different, so their charges will deciding that what is the size, the minor axis and the major axis are the dimension of their major axis and the minor axis. But the shape will be same for this S2S and SO2 type. Now, going to the detail of that, another structure of the molecules. So now the symmetric top molecules. Symmetric top molecules. Because of their axial symmetry, have the polarity ellipse rather similar to those of the linear molecules. So because you have the axial symmetry of the symmetric top molecule, the polarizability ellipse are similar to your diatomic molecules, with this circular cross section at a right angle to this molecular axis. So symmetric top is HC, then you have the Cl, Cl and Cl. So C, Cl, H, Cl, Cl. Now I have a molecule something like that. You have a symmetric top, you have the symmetric axis, this direction. Then perpendicular to this one I am watching in this fashion. So as I said that it is similar to the my diatomic molecules, then you have a ellipse in this fashion. If your field is along the molecular axis, symmetric axis, then you have an ellipsis such and somehow in this representation. Then because now as I said that in the perpendicular across this bond, symmetric bond, in all the direction you have the same polarity, then you have a circular cross section. Now if you look at that again, here this under 1 upon alpha will be the less, then the polarization will be high as compared to this one. So these are the symmetric top molecules. So in this, for such kind of molecules are CH3Cl and H3 are the similar molecules of the symmetric top. So finally, we have another kind of the molecules such as, now these are the molecules that is symmetric top molecules having the polarity ellipse all same as we have in a diatomic molecules. Along the axis you have a elliptical and across it you have a circular one. And finally the spherical top molecules is spherical top molecules. Like in this fashion, this CH4, CCl4, SiH4 have the spherical polarizability surface since they are completely isotropic. And for the incident radiation is concerned, as the incident radiation is concerned, these are the spherical symmetric. You will see that they are not producing any Raman effect because you have an isotropy. If you are changing the direction, because I said that that depending on your how its polarity is changing, that is at least two directions are required. What we have defined is the axial direction, that is the bond axis, or the symmetrical axial, or it's a across of it. So now in this case, because you have a spherical symmetry, everywhere you have the same kind of the structure. So they are not producing. There is no induced dipole moment. If there is no induced dipole moment, there is no Raman spectra. So now we are in a position to discuss that the Raman spectra of the various type of the molecules. Now, once to understand these structures, how the polarizable ellipse is changing and how the dipole moment is induced, then only we can study the Raman effect. Now we are in a position to discuss about this Raman spectra, rotational Raman spectra for the linear molecules and the symmetric top molecules, and we will see that why it is not feasible for the spherically symmetric top or spherically symmetric molecules. So now for today I'm stopping here, and tomorrow I will be discussing that the pure rotational Raman spectra for the linear molecule, and then I will be discussing that this symmetric top molecules for the symmetric top molecules. But the symmetric top molecules, you have a little bit different kind of the selection rules, and I would suggest to you, as I suggested on the previous lecture, that is just to go through some of these study about the symmetric top molecules and the selection rules. Once we are saying that the centrifugal force, the D coefficient we are taking, then you have some additional quantum numbers are appearing, and just to go through that one, then so it will be easier to understand the symmetric top molecules. So, and even I did not much, because that is an isotropic medium, so I need to represent in alpha in some matrix and a tensor form. I didn't recognize, I didn't explain that much in detail, that mathematical part. Just you think that you know much about this polarizability. It is anisotropic and is a tensor one. So you need at least two directions to understand it. So I have defined that along the axis of this diatomic molecule, across of it, and a symmetric to our molecules, a symmetric axis and a perpendicular to this one. So I'll be stopping here. Then tomorrow I'll be discussing that the pure Raman spectra for the linear diatomic molecules and the symmetric top molecules. Thank you.